Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Akmal bin Anwar and I will present about why we choose the bottle rocket. The bottle rocket project demonstrates basic thermodynamic principle by rapidly releasing pressurized air and water. Propelling the rocket upward based on the Newton's third law of motion. It's simple. Design make it useful for various fields such as agriculture, pest control, pressure management, and projectile testing. The release of stored potential energy through fluid upflow into kinetic energy is common in many engineering applications. As the air-water mixture is released, potential energy converted into kinetic energy, generating thrust, while some heat dissipates due to the pressure drop. Aligning with the first and second law of the thermodynamics, this process effectively illustrates energy transfer and conversion in closed system, making the bottle rocket is valuable educational tools. Next, we will go through our problem statement. The bottle rocket prototype provides a framework for testing the efficiency of propulsion system from basic thermodynamic principle. Often systems of this kind can be inefficient in that they do not make the complete transition from energy content is pressurized air and water into kinetic energy needed to propel the rocket. Such inefficiencies are manifestation or incomplete energy transfer, frictional loss, and poor pressurization. That all add to the poor performance of the rocket system and its stability. Many of these inefficiencies identified find their counterpart in real-world issues in industry application, such as the transport of fluid in the oil and gas sector and in the slurry pipeline of mining, where the energy loss increase operational costs while reducing productivity. The fundamental comprehension of the thermodynamic principle is very much vital for engineering technologies design and application because of their eventual transformation effectiveness, which finally affect the performance of a system, often due to inappropriate interpretation of principles such as the first and the second law of thermodynamics, which talk about conservation of energy or energy dissipation. Energy usage can be bad, thus creating excessive waste, and in the end, the large environment format. On the contrary, the discrete for thermodynamics will lead to uneconomical functional cost, unsafe situation, and inefficiency in operation. Concerning the industry, more especially those that cut across areas like aerospace and agriculture, irrigation. Hence, they stand with the almost significant to design the sustainability of engineering system.
Moving to the applications, one of the application of the project is from the first law of thermodynamics, which is energy cannot be created or destroyed, it can only be transformed or transferred. Mathematically derived as delta U equal to Q minus W. And these are the relation of the rocket bottle experiment, which is the first one, energy input, which is compressed air, high pressure and high internal energy. Compressed air inside the bottle has high internal energy stored as potential energy in the form of pressure. Next is energy conservation. When the bottle is open, the compressed air does work on the water, expelling it at high speed. This would represent transfer of energy from internal energy of the compressed air to the kinetic energy of water. And then thrust generation. The expelled water generate thrust according to the Newton's third law. The force of the water being ejected backward propels the bottle forward. The energy of this motion comes from the initial internal energy stored in the compressed air. And finally, conservation of energy. The total energy of the system remains constant, but energy is transformed from one to another. Next is boundary work. The formula of it is W equal to the integration of pressure and dV, which is the change in volume. The bottle acts as a moving boundary when the water is expelled. When the air inside the bottle is compressed, it acts as the first state. Then the air performs boundary work on the water as the air expands and the water is forced out. When the water is forced out, this is where the second state begins. The expelled water gains kinetic energy and momentum, creating thrust for the bottle. As the water leaves the bottle, the volume available to the air increases and resulting in work done by air.
Move on to the ideal gas law, which is PV equal nRT. This happens when pumping air increases pressure while volume of the gas fill space remain constant. Then the compressed air store potential energy, which is later converted into kinetic energy during expansion. When the nozzle open, pressurized air expand, the pressure decrease and air push water out of the rocket. As air expand, its temperature decrease slightly, consistent with the gas law. Then we also have nozzle concept. Nozzle is a small tapered outlet that accelerates the flow of water or gas. Its purpose is to convert pressurized air potential energy into kinetic energy to create thrust. The thrust mechanism happens when high pressure air force water out of the nozzle. The action of water being expanded downward produce an upward reaction force. The nozzle size also affect the performance. With this smaller nozzle creates higher velocity but lower flow rates. Contrast to it, larger nozzle creates higher flow rate but lower velocity. In our project, we have smaller nozzle, which is the bottle cap. It has higher velocity.
In conclusion, the bottle rocket prototype show how thermodynamic principles work in real-world propulsion system. It helps explain energy transfer, expansion, and pressure change, as well as common issues like energy loss from friction. This problem also affect industry like oil, gas, and mining, where energy loss increase cost and slow down operation. Understanding thermodynamics is important for designing efficient system, saving energy, reducing waste, and protecting the environment. Without this knowledge, systems in areas like aerospace and agriculture can become unsafe and inefficient. Thermodynamics help make technology more efficient, sustainable, and cost-effective.